Alright, so let's list down our goals. What is our goal? Is to get from sum of terms to product of terms. That's the transformation we're trying to achieve. And we are going to take, so we saw one method of going directly from here to here, direct method, which is splitting the middle term. We're going to look at an indirect method because this does not work for all examples. Now the indirect method is, I have noticed that if I have a difference of squares, I already have this pathway. I know how to do this. Okay, this is a squared minus b squared equals a minus b, a plus b. So I know how to get from difference of squares to product of terms. So what I'm going to do is I'm going to have to create this pathway of going from sum of terms to difference of squares. So we're going to create this path. Now to create this path, let's go use the area method again. Let's stick with the same example of x squared plus 5x plus 6. Now x squared plus, let me change this just for simplification. It'll make sense why I need to change it. Let's say I have x squared plus 6x plus 8. Let's take these and, if I look at the pieces, what do I have? I have a big square. I have 6 of these. And I have 8 of the smaller ones. Now because I want to write it as a difference of a square, let's start by creating a square. So I create a square. If I want to create a square with x squared and 6x, I would have to distribute these longer rectangles equally. Alright, so I would have to stack 3 vertically and 3 horizontally. But when I do that, I notice that I have 8 small pieces, so I can fill in 1, 2, 3, 4, 5, 6, 7, 8, but I have one missing part. Which makes sense because this is obviously not a full square, right? But that's fine. We are trying to create a difference of square. So what I do is I add one piece, but of course I cannot change what is given to me and also remove one piece. So if I add and remove one piece, I'm not making any change. So if I do that, what does this become? I have 3 vertical stacks, 3 horizontal stacks, and now I have 9 pieces. Subtract one tiny small piece. What does that mean algebraically? This is x plus 3, this is x plus 3, and this is 1. Now if I look at the areas, the area is going to be x plus 3 squared minus 1. Now this is nice. Why? Because I can write 1 as 1 squared. And there we go. That's a difference of a square. And we know what to do with this. This becomes x plus 3 minus 1 and x plus 3 plus 1, which gives me x plus 2 and x plus 4, which you can verify is the same. I'm using the same number of pieces here because this is x squared, say 4 vertical, 2 horizontal, and they fit in exactly 8 pieces. X plus 4, x plus 2. Yeah, 1 big piece, 6 long rectangles, and 8 small pieces. So we have created this alternate way of getting to product of terms. Slightly convoluted. We add an extra step, but it's necessary because our previous method doesn't work for all examples. Now I've been saying it doesn't work for all examples, so let me create an example where that's true and it doesn't work. Like in this case, it does work. So let's look at that kind of example next. Let's say I keep 6x, but I have 7 pieces now, right? Now this is a problem. You can check it. You cannot use the direct method. So what I'm going to do is, looking at this, I know I need 3 pieces stacked here, 3 pieces stacked here, 1, 2, 3, 4, 5, 6, 7. So there are 2 missing. There are 2 missing. What I'm going to do is I'm going to add, and then I'm going to subtract. When I add these pieces, I throw them in there, and I get 3 minus 2 of these squares. Now writing this algebraically, that is x plus 3 squared minus 2. Okay, we have a difference, but it's not the difference of a square. Now recall, the week right before spring break, we learned about radical functions. So what we know is any number a can be written as the square root of a squared, because they cancel out. So I'm going to use that trick here to write 2 as square root of 2 squared. What does that mean? Now I have a difference of squares, which is great, because then I can write this as x plus 3 minus root 2 and x plus 3 plus root 2. And that's it. Using our original method of direct splitting, we would never be able to come out with these values. Yeah, because they are it's not possible, because we only look at integer values in that case. But this method, which takes a detour into converting something into a difference of square, helps us solve any equation. Factor any equation, and then of course that lets you solve it as well. So this is the method or the motivation behind it. And in the other set of videos and in the textbook and anywhere else, this method has a name. It's called completion of square. Right, and then you look at this number and you half that number and so on and so forth. But you can think of it just visually and it might help. The only trouble in thinking about it visually may come in when you have an odd number here, let's say this case, but it's still fine. What you can do is you can split one of the long rectangles into halves. So I want it to be a square, so if I put 2 here and I put 3 here, it's not going to be a square. So what I'll do is I'll put 2.5 here, and I'll put 2.5 here, and then I have 3 pieces, so 1, 2, 3. Now I need to figure out how many of these smaller half pieces I need, right? So let's complete this square. So the dotted ones are just the missing ones. Now remember, this is 2.5 and this is 2.5. So how many ever small squares that you need are going to be 2.5 squared, which is 6.25. Comparing that with 3, what you need to add is that there are 3.25 squares missing. Okay, that's all you need. So what you do is you add 3 1/4 of small box and you remove 3 1/4. Then you look at the square, it is x plus 2.5 squared minus 3.25. And don't worry about this number, because you know that the trick is to write this as the square root squared. And then you apply the difference of squares to factor it. Okay, so that's sort of like the visual understanding or pathway we take for factoring these. Now in the next video I'll talk about another method which you may or may not want to use, but it's a rather recent method of factoring.